I'm Dr. Anup Biswas, Assistant Professor of Chemistry, Hooghly Women's College. On behalf of organized committee, I welcome all the participants and the speakers of 2 days national level webinar entitled as Recent Advances in Chemical Sciences, jointly organized by Department of Chemistry and Internal Quality Assurance Cell of Hooghly Women's College. This 2 days webinar will be conducted in 2 technical sessions, today and tomorrow, and 4 lectures will be delivered. Right now, I would like to request our HWC coordinator, Professor Dr. Samolina Goswami, for her speech. Dr. Goswami, the platform is now yours. Thank you.
Thank you, Anu. Hello, everyone. A very good morning in the first day of 2 days national webinar hosted by the Department of Chemistry in collaboration with HWC of Hooghly Women's College. It's my pleasure to welcome you all to the inaugural issue of Recent Advances in Chemical Sciences. These are truly exciting and challenging times for the field of chemistry. Increasing problem complexity warrants extensive on individual subdisciplines within chemistry. Chemistry has an important role to play in achieving a sustainable civilization on Earth. Chemistry is key to diagnosing pollution sources, designing efficient control strategies, and developing pollution reduction technology. Among the research trends, most important are drug design and development, battery technology, microplastic pollution, green chemistry, agrochemistry, flow chemistry, nanotechnology, etc. The chemical sciences have the potential to solve many of the world's greatest challenges. Chemistry may need to be increasingly interdisciplinary, and there could be a significant shift from blue skies to problem. Chemical sciences will be required to solve challenges in energy, especially in alternative energy sources and climate change, food production, crop production, and clean water. Chemistry might have an increased role in biochemistry, pharmaceutical industry, and biotechnology. We exist in a rapidly changing and turbulent world. Developments in technology, science, and society have caused major changes to traditional systems and structures. These trends are changing the nature of chemistry as a discipline, the role of chemists, and the landscape within which we work. Increasing interaction between chemistry and other subjects was identified as the single most important for the chemical sciences over the next 10 to 20 years. As for all sectors, the global landscape for the chemical sciences is shifting rapidly. 1 minute, please. I repeat, as for all sectors, the global landscape for the chemical sciences is shifting rapidly, driven by technological, economic, political, social, and demographic factors. Emerging economies are investing in research and development, and new economies have recently grown to rival traditional bases of chemistry in both scale and skills. Governments may need to change their funding approach towards more and better directed investment in chemistry. I'd like to convey my greetings to Dr. Madhusudan Maji and Dr. Konok Roy, the eminent personalities and distinguished speakers of today, for being with us. Once again, I welcome all the faculty members, scholars, and students for their participation in such a contemporary scientific issue and request patience hearing. Thank you all. Next, over to Onu.
Thank you, Professor Samolina Goswami, for her speech. Right now, I would like to request the patron of the webinar, our respected principal, Dr. Hima Banerjee, for her speech. Dr. Banerjee, the platform is not yours. Thank you.
Thank you, Onu, and thank you, Shamolina. Shamolina, you have given a beautiful preview of the webinar today. Now, I welcome all the participants today, all the students, the faculty members of the Department of Chemistry, and the eminent speakers of today's webinar. Now, I will give my few words regarding this webinar. During this pandemic time, we all are confined in our home. The college is organizing a series of webinars for different subjects to boost the skill power of the students who are far from college rooms for a long time. I am glad to welcome the participants and eminent speakers in the 2 days national webinar organized by the Department of Chemistry, Hooghly Women's College in association with IQAC of the college. The webinar will cover different aspects of chemical science which will be helpful to the students, researchers as well as the faculty members. The teachers have been designed the lectures have been designed in such a way which will focus on some basic concepts of the subject with glimpse on modern research so that the young educational students can be acquainted with the updates about the topics. I would like to thank the speakers who agreed to share their valuable times, their research works to us in this webinar. Thank you all once again. Now over to Onu. Please proceed.
Thank you, our principal madam, for her speech.
শ্যামলীনা তুমি মিউট করো
হ্যাঁ করছি আমি কম্পিউটারটা ল্যাপটপটা খুললাম
Right now, we will start our first technical session of the webinar. This technical session will contain 2 plenary lectures. Before going to the introduction of the speaker, I would like to request all the participants, if you have any kind of query or question related to the subject or the topic, please drop your query in the comment section of the YouTube. It is my great pleasure to introduce the first speaker of today's session, Professor Dr. Madhusudan Maji from Indian Institute of Technology, Kharagpur. Professor Maji did his BSc with honors in chemistry from Narendrapur Ramakrishna Mission Residential College, securing first class second position. And then he moved to Indian Institute of Science, Bangalore for her master's degree. After completing his master, he received a prestigious NRW Graduate School of Chemistry Fellowship, and he moved to University of Münster in Germany, where he joined Professor Armido Studer's group for his PhD thesis. He received his PhD on organic chemistry, and then he moved to Aachen University to join the research group of Professor Magnus Rupin, and he received a very prestigious Humboldt postdoctoral fellowship. In 2013, he moved to University of Berlin for his second postdoc with Professor Martin Österreich. In 2013, he came back to India to join as assistant professor in the Department of Chemistry, Indian Institute of Technology, Kharagpur. And in 2019, he promoted to associate professor. Professor Maji's work is basically focused on organic synthesis, synergistic catalysis involving metal and organocatalysis, CH bond functionalization, and carbazole chemistry. Very recently, Professor Maji has received the Faculty Excellence Award at Associate Professor level in IIT Kharagpur. Today, he will talk about CP* cobalt-3 catalyzed CH bond functionalization of ketones and amides. I would like to request Professor Maji to deliver his lecture. Professor Maji, the platform is now yours. Thank you.
Thank you, Anu, for your very kind introduction. I like to thank Professor Seema Banerjee and also head of the department, Dr. Sadhan Paramanik, and also Anu, my very good friend, for giving me this platform to talk in front of you. I also like to thank Dr. Samulina Goswami for your deep insight about the chemistry, and I really enjoyed that. So I am now starting my presentation by sharing my screen. And if any issues comes, please let me know so that I can try to sort it out. So I'm sharing. So this is, so I hope I am audible, right? Okay.
Yes, you are audible.
Okay, thank you. So let me start with my presentation. So I'll be talking about 40 to 45 minutes. So I'll not go beyond 45 minutes for sure. So let's start my work presentation. So in IIT Kharagpur, our group mainly work on two major areas, followed by their, just a minute. Yes. Yeah. So we work on mainly two major areas. One is CH bond functionalization, which is a very hot topic, and there are a lot of opportunities. And another important areas we are really heavily involved are mainly heterocycle chemistry, where we work on carbazole, indole, pyrrole, and related alkaloid synthesis. So today I will not discuss about this part. I will discuss mainly about CH bond functionalization, particularly focusing on the cobalt catalysis. If we check the classical versus CH bond functionalization, so why this area is emerging so quickly and so many people are interested? Okay, so let me discuss in a very simple way. We know the aromatic amines are very important functional group. If you check the classical way of preparing them, first what we do, we take a aromatic hydrocarbon, do the bromination first, and then we do a cross coupling. Let's say Buccal Hartwig cross coupling reaction. But with the CH bond functionalization, what we can do, we can directly functionalize this so-called inert CH bond to the amine. Okay, so this is a very simple way. So here you have to do in a step way. You have to do what two steps. So it will be step economic if we can do directly. Not only that, there are in any organic molecule, we know it mainly consists of carbon, hydrogen, and oxygen. So there are several CH bonds available. So if you can do selective functionalization, it will be really interesting one. And also we can do very much kind of late stage functionalization. So you can do at the end and directly put a functional group on a molecule. So this will be really interesting one. So like here, as I told, with the classical way, you can do functional group 1, then functional group 2, and then finally you achieve your product. But with the CH bond functionalization, you can do directly these reactions. But there are some issues. If we consider the CH bond, these are quite stable. Let's say methane CH bond energy, it is 105 kilocalorie per mole. For isopropyl, this is 99. Let's say for the benzene one, this CH bond around 113 kilocalorie per mole, and for acetylene it is 133 kilocalorie per mole. So this side, most of the CH bonds are quite stable because they have a high bond energy. They're quite stable. But if you check, when we study in our book, we check that alcohol oxidation, addition to a Grignard to aldehyde. So we mainly work with the carbon-oxygen bond or carbon-carbon bond. Let's say you are doing a Michael addition. Or you can do the Grignard reaction. We can generate Grignard from alkyl or aromatic chloride or bromide or iodide, like this. So this is the bond energies which are much less compared to the CH bond. So the functionalization of the CH bond will be really difficult because they are quite stable. So today, if I discuss in details about the mechanism of the CH bond, So there are two major mechanisms which I will mainly discuss about the outer sphere mechanism and inner sphere mechanism. I am
Professor
discussing.
Majid,
Yes.
Professor Majid, sorry to interrupt you. Can you please zoom in the slides a little bit more?
This is the full.
Okay. Okay, then please go ahead.
Okay. So this is the full screen in my computer. Okay. So let us discuss about, because I am sure there will be many students from the colleges are listening to this lecture. So I want to give a bit mechanistic details about the bond, and I'll try to explain whenever it is possible, bit in the basic level. So let us discuss about two type of major reaction pathway, like outer sphere mechanism and inner sphere mechanism. In the outer sphere mechanism, what happens here, the ligand mainly active for the CH bond functionalization. The CH bond don't directly interact with the or react with the metal. So metal generally stays kind of not involved much. So like here, this X can be oxo compound for the hydroxylation of CH bond. It can be nitrogen when X equal to nitrogen, or it can be carbene when X equal to C, carbon. So there are two type of this type of insertion possible: direct insertion, where it is 3-member transition state form, and we get the CH functionalization. And also hydrogen atom abstraction and rebound, this type of mechanism also possible when it's kind of radical pathway. So it's hydrogen abstraction followed by a radical attack, and you get the functionalization. This is the outer sphere mechanism. And one of such reaction can be explained with this example. You have a diazo compound which can be inserted to the CH bond using this outer sphere mechanism. This is intramolecular. Actually, after reaction, this become ligand to the metal, and this ligand do all the reactions. Okay, it can be intramolecular insertion or intermolecular, depend on how we are doing that. But we are mostly interested in the inner sphere mechanism, and that also can be divided into three major areas. So a metal which is in the low valent oxidation state, means which is electron rich, it can give electron to this CH bond, and it can undergo oxidative addition. So it form metal, this carbon bond R group actually. In all this mechanism, one thing is common: we have to generate first a metal, this carbon nucleophile. It can be phenyl, it can be alkyl, it can be heteroaromatic, whatever. So it first form this type of intermediate, and there are three ways: oxidative addition, as I already mentioned. Then it can be sigma bond metathesis. What happens? The metal R sigma bond is replaced by this R. Okay, it's undergo exchange, and we get this intermediate. Okay, this is called sigma bond metathesis. Also, where we are working mainly electrophilic substitution. Here, metal is a electrophile which undergo, like your Fidel Cup reaction, electrophilic substitution reaction to this metal, and we get this metal carbon bond here. And then using this intermediate, we can add, these are all nucleophile mostly, and then we can add a electrophile to get the product. So one of such example reported by Professor Bergman, it can undergo oxidative addition rhodium-1, which is low valent low valent state, and then from here several reactions are possible. Okay, what are the challenges in bond functionalization? The first thing is the reactivity. I already mentioned the CH bond are quite stable, and that's the reason the reactivity is an issue. Also, chemoselectivity. Let's say you want to do the one oxygenation on of the CH bond hydroxylation. It should not undergo further oxidation to ketone or aldehyde. So chemoselectivity is also a big challenge. And regioselectivity. In a molecule, there are several CH bonds. We want to do selective functionalization. So that is also another challenge. And also stereoselectivity. So how we can generate, when there is a stereogenic center present in the product, how we can make that product as a single enantiomer or a single diastereoisomer. So that is a really challenging one. I'll now come directly to our work here. So I want to start why to work with cobalt. Okay, so cobalt we are interested mostly. Of course, we do some work with the rhodium, but at the present time we are mostly focusing on the cobalt. So one of the reason is the price. So if we check the price of the precursors for all the similar type of catalysts like CP star cobalt, CP star rhodium, CP star iridium, all are similar. Okay, the congeners. So if we take this group 7 metal price, so iridium is 14,000 per gram. Rhodium around 33, it can be a little lower, but it's quite high price. But cobalt one is only 560 rupees per gram. So if we check the price, cobalt is very cheap compared to the rhodium and iridium. So that is one very important factor. So we can develop a method which can be more economic. Another interesting property of the carbon cobalt bond, if we think the difference in electronegativity, so this is the electronegativity of the carbon and this is for the cobalt. If you subtract them, you get 0.67. So carbon cobalt bond is very polar. But if we take carbon rhodium bond, this electronegativity difference 0.27 for carbon iridium, 0.35 for carbon ruthenium, 0.35, and palladium also same. So for the carbon cobalt bond, almost the electronegativity difference is double. So it is very polar compared to this all other transition metals which are heavily used. But a different reaction are expected, particularly like your Grignard addition to the aldehyde or imine. So this type of 1,2 addition are quite feasible or more possible for the carbon cobalt bond. Not only that, if you check, because it is in the first first row in the D block element, so cobalt has a small ionic radius compared to the rhodium or iridium. So cobalt has more small radius, so it can be accommodated in a sterically congested areas also. So all these factors boosted the community to take cobalt as a major metal for the catalysis when possible. All right, so I'll be mainly focusing on this catalyst, and this catalyst is not really new. So this cobalt 1 complex was synthesized by reacting this CP star ligand. This is called CP star actually. Every time you're writing CP star, this is CP star, okay? This CP star ligand actually can be reacted with dicobalt, this octacarbonyl compound, and it gives you cobalt 1. And this intermediate is quite unstable and it undergoes oxidation quite rapidly with oxygen. This is not a stable one. But if this intermediate, this is actually published by King et al. In 1967, so more than about 50 years, okay? And then if this intermediate can be oxidized with the iodine, it gives you the cobalt 3. This is a bench stable compound, okay? This is really interesting one. This is bench stable compound, and this can be used for the catalysis. At the first time, Professor Kanai and Professor Matsunaga from Japan, they have shown, they are actually pioneer in this CP star cobalt 3 catalysis. They made this cationic complexes and used for this 2-phenylpyridine as a substrate for the directed addition to the imine. Okay, this is the first work. And later on, they also showed that these catalysts can also be used. Okay, this is very easy to synthesize, and since then, this become the choice for most of the chemists, these catalysts. And in India, also there are several groups like Sindoraju, our group, Prabhu, Anvarsan, and so on. There are many people are interested, but quite a few groups are heavily involved in this. Yeah. So there are some internet issues, I guess. So conjugated materials. Now let us go for our result. If we think we started our chemistry with comparatively less challenging polyvinyl aryline moiety, because this is very important molecule for considering the LED devices. Okay, nowadays this is very important area in organic materials. So we thought if we can add this alkyne across this CH bond via hydrogenation, we can either get this monoalkynylated product or dialkynylated product. We are successfully could get this one. A reaction was quite robust. It can work under air, and it doesn't need very special precursors. So by just using 5 mole% catalyst and 1.3 equivalent of the alkyne, we can get this product. By using 10 mole% catalyst and 2.5 equivalent of alkyne, we can get this di product. So reaction work with several examples. I'll not go details like electron-rich aromatics, electron-deficient. Also, when two different aromatic groups are there, so we can get around 5-to-1 regioselectivity, and this work quite efficiently. As I told, our interest was to get this type of polyaromatic hydrocarbon. So this is not easy. If we take this biphenyl derivative, there are these 4 CH bond. We can do the hydrolysis. This 4 in one spot, we can get these 4 reactions. Okay, and if we can couple this bond, so we can get this material. Here we could not get success, but we get this product. So we need to work more on this to get this product in our hand. Another interesting molecule, we know benzofurans, which are very important because they show excellent biological activity. Like this one antipyretic agent, this one anti-estrogen agent, this is inhibitor of mTOR signaling agent. So there are so many are there. So we thought, can we use our hydrolysis in intramolecular fashion this reaction done. So for that we took this amide having a hydroxy group at the meta position. If we tether a alkyne here with a either CH2 or a ester group or carbonyl group here, so we can either get this benzofuran by 5-exo decyclization, which is a favorable reaction, and followed by isomerization gave us 21 example of this product with up to 90% yield. Also, if we have this ester here, we can get this product also quite high yield up to 92%. Another interesting reaction we developed in this paper, what we did, we took another alkyne in the mixture and reacted together. So this side, because intramolecular, this undergo one CH activation, and another alkyne, if we take that also undergo hydrolylation here. So we can get highly functionalized benzofuran in one pot. Same way we can do the hydrolylation and alkylation here. We can do the hydrolylation, allylation here. We can do the hydrolylation and amylation. So in one pot we can get highly decorated benzofuran derivative. And this work was highlighted as a cover picture. And this picture has been drawn by one of my students, Mr. Samrat Kundu. He's an excellent painter as well, along with being a chemist. Now, after developing a reaction with the amide, and our group was set to take a little bit challenging substrate. We know the ketone is so important because ketone can be used for several purposes. Okay, we have studied from higher secondary onwards. But there are some problems with a ketone. What is that? If we have a enolizable proton, it can undergo aldol reaction. This enolizable proton means enolate formed, it can undergo Michael reaction. Like here, not only that, this enolate can be oxidized under, if there is an oxidant, to get this dimer or a hydroxylation. So these are the side reactions which are possible with the ketone. Not only that, ketone is comparatively, compared to amide, it is a bit less Lewis basic. So it forms the cyclometallic species which is less stable. Okay, and when this is less stable, doing reaction with these cyclometallic species will be more challenging. But if we can do, there are a lot of opportunities. What are those? We can get immediately like this amylation product, alkylation, allylation, so many. Okay, we can easily get it. So this is the work we took next. And also we check carefully in the literature that ketone directed halogenation, hydroxylation, amination, all are reported. But for the CC bond formation, only alkylation, alkylation, and arylation reported. So alylation was not reported. With the ketone directed arylation, we reported first time using this cobalt catalyst. As shown here, the reaction work up to here 33 example and 6 example. Means this reaction is very broad. It work with the indole, it work with several ketone. Like here, when you have an N-alkyl chain, this product can be obtained in 60% when you have a study butyl sterical hindered group, we get 81%. Also, with a electron withdrawing group here, it can be work. We can change the allylatic agent, benzofuran type of derivative can use naphthalene, anthracene, indole. This reaction can also be done in gram scale. Not only that, this is a natural product called metachalcone. This can also be synthesized using our method. Now let me discuss a bit about the mechanism. So I would request students to listen very carefully here. So if we check two of these in a one-to-one mixture, okay, in the reaction mixture, and we did the reaction, we want to do the competition between these two, who is more reactive. We found this substrate with this product obtained in 7.6 over this one ratio. So this is forming as a predominant product. Why? Because this reaction undergo via this ketone directed electrophilic aromatic substitution pathway. So when it is electrophilic substitution, we know that electron rich substituent will be the better and electron deficient will not be good one. So this is the reason this prove that the reaction undergo by electrophilic aromatic substitution pathway. And also we did the reaction with the deuterium exchange study. What is that? We did the reaction, we did not add allylatic agent, but we added the deuterium source. We did several experiments. We found there is a no deuterium incorporation at the alpha position. So if there is a deuterium incorporation here, so this carbon cobalt bond, the deuterium will be coming and giving you deuterium here. So this is not going backward. So this step, this CH activation step is not reversible. Now another one, we also wanted to do the kinetic isotope study. We have studied in BSc in Peter Sykes, right? So we check here that when we take this deuterated substrate, if the CH activation step involved in the rate determining step, we know carbon deuterium bond are more stable, so it will be giving the product less, which indeed we found by competition experiment. When we found this product form almost 3:1 ratio over this one, and parallel experiment almost 3.8. Okay, not only that, when we take the same acetophenol, we made all these product reagent actually. So with the deuterium here and proton here, we could do intramolecular competition, and we found that this product forms predominantly because this CH bond break quite rapidly and it is involved in the rate determining step. So with this, we have drawn this catalytic cycle. So after ketone undergo coordination to this cobalt, which is a 16 electron species, and this is form, okay, this cyclometallated species. So this is also like this is a 16 electron species, okay. So it has it is hungry for another ligand. So this will be coordinating with this alkene, and this alkene will be undergoing this carbon cobalt bond undergo insertion here, and followed by carbonate elimination give us this allylated product undergoing the regeneration of the catalyst. So this is our catalytic cycle. When you do a reaction, we also want to show its application. So first we did the alylation. We know if you take with the osmium tetroxide, it gives you the dihydroxylation, which can be cleaved by using sodium periodate, followed by treating with the ammonia to get this as a tetracene. Also, we can get this allylated product in a gram scale. Then we did the Walker oxidation to get this ketone, which from here formal synthesis of this alkaloid named anthocyanin is achieved. Also, we can get this isochroman derivative in 74% yield, which is not easy, and we can get quite rapidly in few steps until here. There are several natural products, more than 50 like this, which we believe we can target them for our synthesis by using our method in a few steps. Now I'll discuss, we all know there is one Nobel Prize winning reaction, Heck coupling, right? What do we do with the Heck coupling? We take the aromatic bromide and we take the alkene under palladium 0. Okay, it will be reduced to palladium 0, and then we get the alkenylated product. So like this one, this product can be obtained 95%. So if you want to do the alkenylated arene, so Heck reaction is one of the reactions, but for that you have to start with the pre-functionalized starting material. So another reaction, this is also an old reaction, is called Fusio or monetary reaction type. So this reaction, we can also do the one, it reported that alkynylation can be done on the CH bond. But particularly for the Heck type of reaction where you need a functionalized aromatic compound. But if we can do this reaction by CH alkynylation, then you don't need, you can directly use CH bond and do the functionalization, which indeed work with the cobalt catalyst with a ketone directed. We can take this acrylate under using a oxidant, so oxidative coupling this is, and we can get up to 30 examples, 76% yield. Several examples like phenyl can be used, like simple acetophenone. We can have a electron rich disubstitution, free phenol, electron withdrawing group. Then there are also, when you have a two different benzene, the electron rich side work preferentially. We can have the chalcone, thiophene. Also, the electrophile can be phosphonate and also sulfone here, phenyl sulfone. So there are several examples which can be used. And also, when we tried to make this cinnamic acid derivative using this acrylic acid, this did not work, okay, with a free carboxylic acid. We thought if we just take its surrogate, okay, this terbutyl group, which can undergo after the alkynylation, this will be CO2 terbutyl. And after the alkynylation, this CO2 terbutyl can undergo hydrolysis where butane gas will be going away. So we can get this alkynylated product, this cinnamic acid, we need what? We have 5 examples and we can get this product in good yield. I would say moderate yield here. Not only that, if we take a vinyl sulfone, there are 2 CH alkynylation possible. So we can first put the electron deficient one, so one work, and then in one pot only, we added another aromatic ketone, this one, and we can get this highly decorated vinyl sulfone derivative. Now also, we can make this product in grams, and then using with ferric chloride, we can create this coupling. It's called this product called gamma PTAR antagonist. So we can make this product in only 2 steps from these starting materials. This also shows the application of our method. Another very challenging reaction is the vinylation. We know styrene derivative is quite unstable, particularly if we take the styrene and keep it under the, let's say, Bronsted acid or under any acidic condition or base condition, they undergo rapid polymerization. So Professor Chatterjee also reported this using this catalyst directed CH vinylation, using this as a vinyl surrogate. But problem is this I would say problem, but with this ruthenium catalyst, this is quite unstable. So if we want to develop a method using a cheap starting material like vinyl acetate, and using this one, can we do the vinylation? Okay, using a air stable fast road transition metal like cobalt catalyst and base metal catalyst, which indeed work well. And this work as shown here, we can take this ketone and vinyl acetate, we can get this vinylated product. Here with this with the electron reach this substituent, we can get this vinylation. We can get this with the free hydroxy, this vinylated product. These are all stable under the reaction condition. That is what we are really happy. And also we can have this thiol here, thiol methyl sulfide, which also known as a catalyst poison, but here it doesn't give us much problem. And if you want to do the vinylation of the aromatic bromide or halide by Suzuki coupling, this type of bromide or chloride may not be surviving, but by this directed one we can do this. So this is also an advantage for this. Carbazole can be vinylated. So these all examples are here. Also chalcone with the dimethyl here, with this chalcone with a 1,3-diene. So this scope is quite interesting and quite broad, and we can make this product in considerable amount. Like Fujiwara-Moritani reaction, this is a different reaction. Here you don't need any external oxidant. Here this can be your oxidant as an electrophile. So it undergo 1,4 addition followed by elimination, and we get this one. Okay, and this type of acrylate, the cinnamic acid ester derivative can be synthesized in a good yield. Like this one is 67% yield. So yield was moderate, and we have good number of examples. Another interesting area we are working is the synthesis of the alkaloid by developing our own reaction method. So one of the series of alkaloid we are interested in the synthesis of this acridone series of alkaloids. So these are all acridone series of alkaloid. They show interesting biological activities. So we want to make some of them. We have so far achieved photosynthesis of 5 of those alkaloids. I'll tell how we did it. Before that, let us discuss about the amination reaction as discussed earlier. So generally, if you think you want to do the amination of the aromatic to get this type of product, you can do the called Hartwig-related coupling reaction. Also, amide can be synthesized like this. This is a classical method by doing these cross coupling reactions. But we want to do this amination using a CH amination. So to get this type of natural product, we have to generate this chemical. For that, we want to get a nitrogen which will be equivalent to this electrophile. This means it will react with this both sides. Okay, 2 electrophiles. This will be acting twice. So if we can get, we will get this product, and from there we can convert this to our other natural product. For that, we have to develop a ketone-directed CH amination method. As shown here, ketone-directed CH amination with this oxazole we have developed, and it works with excellent scope up to 91% yield. And also to compare the reactivity between the cobalt and rhodium, we did for the every example we did the reaction with both the catalysts, and I'll show how they are complemented. As shown here, with this one, for this substrate, cobalt give us only 56% with the cobalt catalyst, C-crystal cobalt. Okay, with the rhodium it was much better, 72%. With this one also 76 with the cobalt, and for the rhodium it is 88%. And so on. When we took the electron-rich substituent on the aromatic ring, we found the rhodium is the winner. However, cobalt also provided us the good result. At the same time, when we have taken the electron like a chalcone case, cobalt gave 68 and rhodium only 40%. So cobalt was much better and winner here. When you have a chlorine and bromine electron withdrawing group, rhodium did not give us product, but cobalt gave us at least some around 40% yield. And for this one, cobalt gave 91% yield, but the rhodium only 20%. For the carbazole, rhodium did not give us product, but the cobalt gave us 66% of the product. In a similar way, we can have this both side electron rich side emulated preferentially. We can have several of these substitution on this emulating agent. We can use the aliphatic one. For this case, rhodium was better compared to the cobalt. We can also have the heteroarabatics. So we found in some cases cobalt better, some cases rhodium better, but cobalt gave product for almost each and every substrate. Our main motto was to prepare this natural product using our method. For that, we took this substrate, we did the amidation. This gave a mixture of vigioisomer around 3:1 ratio, which we took and did the hydrolysis without isolating them, without separating them. So then we got this free amine derivative. This is as a major, this is as a minor. We took both and we treated under potassium tertiary butoxide in DMSO. We got this natural product, tododioxin A. From there, by protecting this NH with the MOM chloride, we got this tododioxin D natural product. To get this arborenin natural product, we took this one and did the methylation as shown here. With this methylated product, we did the hydrolysis to get this methylated aniline derivative. By copper catalyzed CH amination, we got this intermediate. From there. This ketone directed selective demethylation, which was already reported in the literature. So this ketone will undergo coordination with the BBRT and selectively only deported this O-methyl, leaving other two intact. We got this arborenin natural product. I'll not go details about these two natural product synthesis. So using this one, we have made this intermediate using cobalt catalyst over 4 steps, and from there, formal synthesis of this actinisin and noractinisin natural product has been achieved. Not only that, we can take this amidated product and using under reductive coupling, we can couple this ketone with this ketone with this amide. We get this 2-phenyl 3-methyl indole derivative. We can also take this one to get this quinolone derivative. From there, by treating with the BBRT, we got this anti-tumor agent. Also, by treating with POCl3, we get this 4-chloro-quinoline derivative, which upon treatment with amine, we got this 4-aminoquinoline derivative, which is a potent cytotoxic agent against H116 cell. Also, we can get these heterocycles and also this one in 85%. So, what I want to say, this product has really valuable, and we can prepare several other heterocycle using this product we made by one step using the simple ketone as a starting material. So, this work was highlighted as a hot paper in chemistry European journal last year. Also, this was one of the most downloaded paper in that year, in 2009. Again, in the mechanism, we did the competition experiment, and what it shows that electron-rich aromatic ketone reacted preferentially over this electron-deficient one, around 4.5 to 1 ratio. So, the reaction will work under base-assisted intramolecular electrophilic substitution pathway. Also, when we did the deuterium scrambling, like earlier case, it did not undergo any deuterium incorporation, or less than 5% only. So, in this case, it gives us the hints that CH activation state is not rate determining state. Also, we did this and this as a mixture in the same reaction vessel. Also, we did the parallelly and then mix them together. The both competition and parallel experiment shows that kinetic isotope effect value around 4.6 for the competition experiment. For the kinetic parallel experiment, the KH by KD value is around 4. So, CH activation step involved in the rate determining step. Okay. We also tried a lot to isolate some of these intermediate, and it was not really successful to isolate them because this cobalt carbonyl bond is quite polar. As I told earlier, this undergo rapid protonation, and we don't have glove box, so that's where we really struggle. But in LCMS analysis, we could detect the molecular ion peak having this mass. Okay, so from there we can say that LCMS analysis supporting the formation of this intermediate, and we have done several experiments. I'm just showing only one, but we have really nice. So this type of intermediate can be detected by LCMS analysis. Yeah, sorry, there was some internet issue. So now if we take this ketone and if we take this intermediate here, and it will be, if we check this catalytic cycle, this ketone will be undergoing the coordination to give this LCMS, this intermediate, which is supported by LCMS analysis, and also this LCMS, this is 16 electron species, so this nitrogen will be undergoing the coordination with this cobalt, and this carbon cobalt bond will be undergoing the insertion to this NO bond, and here carbon dioxide extrusion is going away to give this intermediate, from where protonation will give us this amidated product. Then we can get this one. So we can get this amidated product here. If we check the binaural derivative, so this binaural derivative is really valuable. So this is the binaural derivative is the one of the most used or the best ligand for asymmetric catalysis, this chiral scaffold. Not only binaural, from there this is called binac. This is also very important ligand for palladium catalysis, hydrogenation, everything. This is very important ligand for the asymmetric CH bond functionalization, this carboxylic acid. Also, this has been used for the Mannich type reaction. This is a boosted acid, phosphoric acid, and I myself also work a lot on this area. And this has lot of use, and still people are using a lot. This is also used for selective alkylation. This is for the another boosted acid. This is for phosphoramide ligand for asymmetric alkylation. We know this is Marwalker phase transfer catalyst. This is the secondary amine, and this is for the. So means this type of binaural derivative very important, and you need to substitute here. And this is not always easy. Okay, so if we check how we achieve this type of amidation, as shown here, if we take this anilide and if we take imidamide, and this can be used as a if let's say imidamide, so this type of reacting group has been heavily explored in stage functionalization. But if we take this carbonate or thiocarbonate, this is comparatively less explored reacting group. But if you take the butyl lithium and in TMEDA, okay, we can do the lithiation here, and from there we can do the functionalization like this one. Okay, so what happened here? We take the butyl lithium and it undergo deprotonation, and then from there we can get this lithiated species, which will be used for the CH bond functionalization. Just a minute. And if you take this binol and you want to do this functionalization, you have to take this butyl lithium and then you have to generate two-fold deprotonation. You have to get these two negative charge on the same molecule, which is always a problem when you have a trace of moisture. What happened here? It also forms the monolithiated product. So if you get the mono and difunctionalized product, their separation is very difficult. Okay, and that give a lot of trouble, and our group also faced a lot of trouble on this. So we thought, can we develop a method where we can simply use this carbonate as a or thiocarbonate as a reacting group for the amidation or alkylation reactions, which will be really interesting one, which indeed work well. If you take this thiocarbonate with a alpha fluoro, so we can get this product up to 64% yield. If we can do the 2-fold CH amidation up to 66% yield. If we have one reacting group, we get this amidated product on the binol derivative, which is our main target, with up to 90% yield. With octahydrobinol, we can get this monoamidated product 72% yield. We can also get this diamidation product 78% yield. This is a very challenging product, and we are really happy. It has a huge application, okay, as a catalyst design. So this already we have achieved 78% yield in one shot. Okay, this will be really interesting one. Also, we can do the biphenyl. This is also excellent chiral ligand or the scaffold, where we can do the either monoamidation or diamidation. Also, we can take the spinol. This is another privileged scaffold for the asymmetric catalysis. We can do the diamidation up to 67% yield. We can take this tyrosine derivative and we can do also the amidation. Another way to get these alkylated arenes are Kumada coupling reaction. We all know that Kumada coupling can be done using palladium or nickel catalyst to get this alkylated product. Also, we can use this another Nobel Prize winning reaction, Suzuki cross coupling reaction, where you take this functionalized aromatic halide and we get the boric acid and we do the cross coupling. So, like to get this product, we can get 94%. But you have to synthesize this boric acid, which need a lot of effort. At the same time, we need to take this functionalized aromatic iodide. But if we can do the CH alkylation, it will be really interesting one, because we want to develop this type of materials quickly. So using this carbonate, we can do this alkylation, and also we can have the alpha position of the methyl with the iodide you cannot do coupling with this type of iodide. It will undergo reaction. It will not be free. So that will give you complications. We can have the biphenyl, we can have the binol, we can have the this type of di-alkylated product. Some minor monoalkylated product are also isolated in 4:1 ratio. For same for here, we get the mono and also little bit di also from. We can take this ketone derivative. So this type of product can be synthesized quite readily. There are some interesting observation we found. If we take this substrate with the X equal to sulfur, okay, this di product, okay, it gives you the diamidation quite nicely. If X equal to sulfur, this alkylation did not work. Okay, only X equal to sulfur, this diamidation worked. At the same time, if we take X equal to oxygen, amidation did not work. But X equal to oxygen, alkylation worked. So what is the problem? Why thiocarbonate is giving amidation selectively and carbonate giving the alkylation selectively? Also here we took the mixed one. We make one side thiocarbonate, another side carbonate. For this one, amidation work, okay, from here. But it did not give us alkylation, although there is a carbonate one. Also, when we take this substrate and use this one, there are no alpha hydrogen there, so no CH activation possible. So this sulfur undergo coordination, I'll tell you in the catalytic cycle, so that stops the reaction. What is the problem here? So first, for both cases, this type of intermediate has to form for the reaction. And here, this sulfur will also coordinate to this carbonyl group, okay? And this sulfur as coordinating to the carbonyl group, it will be another substrate actually like this coordinating, and this nitrogen has to coordinate it here. So the substrate has to kick out of this coordination. For nitrogen it is strongly coordinating, so it has enough power to remove this sulfur from here to get this type of intermediate, okay? But when it is for this case, story is different. When you have this acrylate cannot kick out, that remove this coordinating sulfur, okay, because it's very weak, okay, to replace. So alkylation did not work for this thiocarbonate. But for this carbonate, problem is the carbonate is a weakly coordinating, and carbonate, and if we take this emulating agent, this nitrogen probably directly attack to the carbonate, this cobalt center. For that, what happened? We don't get this intermediate here. It cannot coordinate. Okay, so because of that, it doesn't form in presence of this isoxazole. It doesn't react. So we don't get this intermediate. So that's a problem. But for the carbonate work, both are weak. So it can be in competition. It will be the alkylation product. So main reason is the coordination ability, the competition. Because of this emulating agent is much stronger compared to this one. And between these two substrates, thiocarbonate is much stronger coordinating agent than this carbonate. Another one is the amide product. We know the amide are very important not only in the protein and enzymes. Also, if we check the drug, 25% of the synthetic drugs consist of an amide unit as shown here. Okay, so synthesis of the amide is very interesting one, and we thought, can we use our CH activation strategy to make this amide? We know for the amide synthesis, we take the carboxylic acid, we activate that using, let's say, DCCI as the agent, and then we use the amine to get the amide. But here, using the rhodium catalyze, we can do the directed CH amidation directly with up to 25 example, excellent yield, and it has a really nice functional group tolerance as shown here. We can have the free aldehyde here, we can have bromine with fluorine, free NH group, free phenol group, all are working with nicely here, free phenol group. We can get all these amidation product. Another interesting project we are working, this is the last work I will be discussing. So here, enamide is very important building block or functional group present in several natural product as shown here, several natural product, the Z enamide. We thought this amidation, whatever I discussed earlier, like this one, if we don't take this emulating agent, we only take the isoxazole having no benzene here, okay, not benz isoxazole, only isoxazole, and we can insert to this NO bond. So this will give us directly this Z enamide, and this Z stereochemistry should come because this is already this C double N and this oxygen are already in the Z form already. So we can use that and we can get this Z enamide. This is a nicely executed by one of my students, Wonkar, and it worked really nicely up to 33 example. Only few are shown here. We can have the free NET2 phenol, of course, it's a reacting group here, bromine, ester group, chlorine. We can have several functional group here, also aromatic group phenyl here, also heteroaromatic. We can have the alkene here. We can have this type of aliphatic group, dialkene, and also we can use the tyrosine derivative. So what I want to say, this enamide can really, we can generate in a very mild condition using a rhodium catalysis. So allylation is also very important reactions, particularly if we think about the two allyl amine, this amine derivative. So if you want to make them, we can do a lot of natural product synthesis. Not only that, this allylation or phenylated product are also key building block present in several natural products. Okay, so how we did it? If you check this directed aniline, and if you take the aniline as a reacting group and allylation, this has a problem. This double bond may undergo isomerization. You get a mixture of products. This is one issue. Another issue is after allylation, if this nitrogen can undergo hydroamination to get this indole. We thought if we get this imidamide as a directing group, it will be very strong coordinating. Not only that, if you have this dichromethyl group here, it will be taking away the electron, so it will also help to release the catalyst as shown here. So like this, we can develop a reaction, and this is my last result. We can do the CH activation even at minus 20 degrees centigrade. We know the CH bond functionalization most of the time need high temperature, and the low temperature means it works mostly at the room temperature, but minus 20 degrees. So this is very activated substrate, and we can do this reaction very nicely. At the same time, we can do the mono. We also introduce this as a new analytic agent, and also we can do the diarylation using this more reactive analytic agent. So with this, I like to thank my group. So this cobalt work is done by Saurabh. He about to get his degree, and Raja, they did the cobalt work, and Subhankar did the rhodium work, what I discussed briefly in the last. I like to thank SARP, Inspire, CSR, and ISRD Startup Grant for the financial support. And I like to thank you all for your kind attention. Thank you.
Thank you, Professor Maji, for your nice presentation and wonderful research work. So I have one from the participant, that what you mean by bench stable.
Yep. Bench stable, yes. So bench stable is something, you know, I'm sharing the screen again, just a minute. Oh, already sharing, right? Anup, it is already
Yes,
in share,
yes.
right? Yeah.
Yes.
Okay, okay. Okay, I also want to mention here, during the time I was a bit confused whether there is internet disruption or I have disconnected. So sometimes I got a bit disturbed. Okay, so bench stable, what I mean, let's say you are taking a bromobenzene, okay? So that reagent we keep in a outside in a cell. Okay, this is very stable. You don't have to store in a glove box under inert atmosphere, which is very difficult. So that is why this reagent you have to store under inert condition. But this one you can just simply keep in a vial or in a bottle and just keep in a shelf. Okay, that is what I'm saying. On the bench it is stable. You keep in the bench and stay for several months, no problem. We make it and keep it, it work well, no problem. That is what I mean, bench stable.
Okay, thank you. I have a couple of questions for you, Professor Maji. Is your cobalt-3 catalyzed CH bond functionalization compatible with Wainwright type of amide? Because
Yes,
amide is very well-known player in CH bond activation.
yes, actually one-day amide might be already someone did it with this one, already reported, but one-day amide is very much possible, and this is one of the best directing group, I would say. But there are a lot of work has already been done, so we did not study on that. Because
okay.
Yeah, of course it is possible.
Okay, and about your highly functionalized benzofuran derivatives, highly functionalized benzofuran derivative, is it also possible to prepare indole derivative in the same way? The nitrogen connected to the alkyne group.
It's a very good question. Thank you. Actually, this was also, we tried a lot with the nitrogen. There are very specific role of oxygen we found for this type of CH bond functionalization. I appreciate the audience who asked these questions. We tried with this nitrogen as well, so we are not successful so far. I won't say it is not
Okay.
possible, but we did not
Yeah.
get the success so far.
Okay. So it was my question. So Professor
Oh,
Maji,
thank you.
okay,
Yeah.
so I have one or two more questions. The next question is that for your carbonyl detected alkylation,
Yes.
alkene group insertion by carbonyl group detected uh,
Yes.
right. So you have here, what I find is that you have only used electron deficient alkene.
Yes, you're right.
Yeah, is it possible to, or have you tried with more simplified pi
We
bonds
tried.
or
We
olefinic
tried.
case?
Yes, we tried with the styrene and this type of, let's say, 1-octane. The 1-octane is difficult. With the styrene, we get some product, but with the styrene type of derivative, it may not be stable. So this type of reaction we call Fujiwara-Moritani type coupling reaction, as shown this one. This is mostly work with electron withdrawing Michael acceptor.
Right.
But our attempt probably we got very minor yield with the alkene, with the unactivated alkene, but yield was not good. Okay, but there are some more development which I did not include here for other directing group, this type of insertion work, and we are working on that, but with this one we did not get success.
Okay.
We tried.
Okay. Okay. And about the very last part of your talk, the rhodium catalyzed reaction, the CH bond activation by rhodium catalysis.
Yes.
So where yes, no, after that, very last, yeah, here in the directing group, you have only used CCl3, a strong, very strong electron withdrawing group.
Yes.
Right?
Yes.
Because it releases the catalyst quickly.
Yes.
Is it the case? So is it
Yes.
compatible other electron withdrawing groups there? Maybe
Yes.
the varying the halogen moiety
Yes.
CCl3 instead of
It's a good
CCl3
question.
CF3.
Yeah, this is a very nice question because we tried if you see the design principle here, we tried with mainly CCl3 because this is very cheap. Trichloroacetonitrile. This is very cheap. So it is bottle reagent we can have in liters. But CF3 is very expensive, so we do not use that. But I believe CF3 may give a different result also, means better result, what I want to say. So this CCl3, yeah, better yield can possible. So actually we wanted to work that time and we switched to other project, CF3. We took that as a serious maybe 4 years before. This is I also want to mention this is the first paper from our research group. So after that we did not do much work here. So but this with the CL3 main idea is to, after the reaction, see, coordination has to be there. Also after one cycle, if you check the catalytic cycle every time, I'll go to one catalytic cycle, let's say this one. This catalyst has to be removed also from the directing group. So for that, if it is like too much, the cobalt, it will not release. So after one cycle, it will stop here. So we need something which coordinate at the same time also go away easily. So this is the reason we could we took this CCl3 here. That is the main reason.
Okay. Okay, I think we have no more questions, Professor Maji. So in that case, thank you very much for your time and for your presentation.
Okay, thank you, Anup. It's excellent, wonderful. Yeah, thank you very much. I hope I did not take much time.
No, it was fine. Perfect.
Okay, thank you.
Okay, thank you.
Thank you.
Okay, so this is the time to move
Okay.
to the second lecture of today's
Professor
session.
Professor Maji, I have a question. Hello.
Oh,
yes, yes, yeah, no problem. Yes,
Hello.
please tell me.
In many synthesis, you have taken cobalt, octa dicarbonyl, cobalt octacarbonyl. Only the key factor is electronegativity difference. That is, you have mentioned that 0.669 carbon and cobalt. Other is any factor present?
Yes, there are of course other factor as I mentioned earlier. Just a second, I'll just share the screen. Yes, then only just a minute. It take 1 minute to get into the slide. So as shown here, there are three factors which is important. Okay, so as shown here, one is the electronegativity difference. So that give a different reactivity. Like when you want to add a like your Grignard addition to the imine or carbonyl, that is more possible for the carbon cobalt bond. This is one reason, electronegativity difference. And one main idea is to use the cobalt because it is comparatively much cheaper. Another thing is the ionic radius. Okay, so cobalt is small. So when there is a sterically hindered site, let's say one want to use a here, okay, a sterically hindered site. So can it be used? So that also some cases possible to observe. Okay, these are the three factors: price, bond polarity, and also the ionic radius.
Okay, another question is that dicobalt octacarbonyl, when undergoes in the in situ reactions, it remains as dicarbonyl octacarbonyl,
No,
or it destroys to oxidations to another
yeah.
cobalt one or
What
cobalt.
happened actually? We are using dicobalt octacarbonyl to make this complex. So it react give this in situ. We are using this as intermediate, a catalyst, our catalyst precursor, I would say. This one.
Okay, okay,
Okay, like CP star, cobalt, carbonyl, iodine. In the reaction mixture, it is very difficult to say what is there, what is not there. Means, of course, some of CP star cobalt is there, no problem. This carbon monoxide goes easily, iodine also goes easily. You can see the silver we are using mostly to take away one iodine to get this cationic cobalt complex. Okay. So if we take as shown here, one catalytic cycle I'll discuss here. So here silver iodide goes away from there. Okay, and we get this CP star cobalt acetate. Okay, acetate is a bidentate ligand. So cobalt is 6 electron, CP star minus 6 electron, acetate bidentate 4 electron, so 16 electron.
16.
From there it undergo coordination. This will be kind of active intermediate. So you can see there is no carbonyl, no iodine, all the things.
Okay, okay. Thank you,
Okay.
thank you.
Thank you, Majid. So here is another question from the participant. For you, the question is that metal complexes with large organic ligands are sometimes not very stable. What is the reason for that?
Metal complexes with a large organic ligand.
Yes, metal complexes with large organic ligands are sometimes not so stable.
See, I don't think the large or small it is a matters for the metal complex to get stabilized or not. Question is it undergo further reactions. If your metal is very reactive, let's say you store under a condition which is not oxygen free and metal is in the low valence state, so obviously it will be undergoing the reactions and ligand will be going away, departing from the metal. Not only that, the ligands can also be redox active. What does that mean? Let's say you use a phosphine with the alkyl substitution. Okay, I have struggled a lot. So if you have a little bit moisture and acid, it undergo hydrolysis. So the ligand also undergo decomposition. So it is, I won't say this is whether large or small, that controlling, I don't think so. In my opinion, it is the reactivity of the metal which undergoes side reaction or reactivity of the ligand which give you the trouble. So it would be not, it would be nice to generalize about the stability and the size of the ligand.
Okay. Thank you, Professor Maji. There is no more question that I can see. In that case, once again, thanks a lot for your question answer session and your presentation.
Thank you very much. Thank you, everybody. So I'll be stop sharing and thank you.
Okay. Okay. Okay, so this is the time to move to the next lecture of this technical session and the last lecture of our today. So the speaker of this session is Dr. Konok Rai. Dr. Konok Rai did his BSc from Narendrapur Ramakrishna Mission Residential College, and then he moved to IIT Kharagpur for master's degree, and he completed his master's in the year 2009, and then he moved to National Chemical Laboratory Pune for his PhD thesis. And during his PhD tenure, he received the Best Research Scholar Award in Catalysis in the year 2014. After completing his PhD, he moved to ETH Zurich for his first postdoctoral position, and from there he moved to Diamond Light Source Laboratory in UK for his second postdoctoral research work. Very recently, he has come back to India to join Banaras Hindu University as assistant professor. His research work mainly focuses on inorganic and physical chemistry, and today he will talk about in situ X-ray photoelectron spectroscopy studies of heterogeneous catalytic reactions. Professor Roy, I am switching the platform, handing over the platform to you.
Hello.
Hello.
Anup, am I audible?
Yes, you are audible. Please
Okay,
start
thank
the
you.
session.
Yeah, thank you. Okay, hello everyone. It's now good afternoon. And thanks Anup for introducing me and all the organizing members for introducing or for giving me this invitation to present on this webinar. Thank you very much. So with this, after this introduction, I am going to present my topic here today, and I will start the slideshow so that you can relate my work with the slides with the visual thing. So I'm going to start my slideshows. So my topic is in situ X-ray photoelectron spectroscopy studies of heterogeneous catalytic reactions, which is a broad subject of my research activities carried out during PhD.
Hello.
And my
Hello.
tell me,
Sorry
please.
to interrupt you. Have you shared the slide?
Probably
Or
not.
not yet?
Probably not yet. Sorry. It should be. Okay. Yes. Okay. So.
Yes. Yes, please continue.
Yes. Okay. So my topic is, as I said, it's an in situ X-ray photoelectron spectroscopy studies of heterogeneous catalytic reactions, which is a broad subject of my research activities carried out during PhD and postdoc. And here, after establishing the group, I will be trying on these kind of different reactions and again on heterogeneous catalytic reactions. So when we talk about catalysts in chemistry, they are fascinating materials. Those participate in a chemical reaction to accelerate the rate of the reaction to produce very selective products. We all know that. And interestingly, out of all industrial catalysts, more than 80 to 90% are heterogeneous in nature. This means that they are they stay in a different phase than they are in a different phase than the reactants, and they can exist. They are fascinatingly important because they are important in many industrial catalytic reactions, like for pollution control, or in industry, like this FCC catalytic converter reactor, or this electrocatalyst, or in batteries, and they come in many different shapes, many different colors, and they can be fitted in different varieties of textures and morphologies to fit into catalytic reactors and catalytic plants. And the catalyst is very amazing materials because they can be doing the same reaction repetitively and over for many cycles without themselves being consumed in the reaction. And to make processes cleaner, greener, or sustainable chemistry, which is a modern demand, we are forwarding toward developing very efficient and very good functioning catalysts. Now, when we talk about improving the catalyst or developing catalyst, we go to the microscopic world of atoms and molecules, where a catalyst binds to a catalyst, where reactants binds to a catalyst surface, and then the reactant molecules bond arrangements, like old bonds are broken and new bonds are formed to make some selective products, and these products are then dissolved from the catalyst surface by freeing the reactive sites, which can again binds new reactant molecules. And in this way, these reactions are happening in heterogeneous catalysis. And these sites of the catalyst, these particular sites which binds reactants or which performs a particular chemical reaction, are called the active site. And this ensemble of molecules together are called the active structure of a heterogeneous catalytic reaction. However simple this video, or however simple this cartoon may be seen, but actual heterogeneous catalysts are much more complex, beyond our imagination, because of different material complexity. Because in catalyst there exists active metal, supports, promoters, poisons, different kind of moieties or molecules or entities which also take part in the reaction. And not only the inherent material complexity of the catalysts, there also exists the pressure gap, which we call in heterogeneous catalysis is a famous pressure gap, which means that the actual reactions are happening in atmospheric pressure or even higher, like 10 bar, 20 bar in industries. But the techniques what we are using to see this catalyst functioning are not operating in that pressure range. So these are called the pressure gap. It means that in heterogeneous catalysis, if you directly want to correlate between the structure and activity of a catalyst, activity means its functioning, it is not very straightforward. And for that reason, we should see a kind of real-time picture of a catalytic reactions. It is not possible to understand an active structure or a catalytic system by studying them in a post-mortem situation or pre-mortem situation. I mean, not in their functioning state. They should be studied in the functioning state, because as I was mentioning, or I am mentioning to you, that catalysts are inherently dynamic materials, and their structure can be different than the structure you see in a different condition. Like in this cartoonistic view, in ultra high vacuum, you see a very layered structure, very layered and very organized structure of atoms of a catalyst surface. But the moment you put the reactants, or you put this catalyst into reactive environment, the atoms are restructured, and they produce a completely different kind of surface or different kind of structure. That's why, particularly for heterogeneous catalysis, I am mentioning this because the topic of today is heterogeneous catalysis, but not only heterogeneous catalyst, many of the systems needs to be understood or needs to be investigated under in situ conditions. So by in situ, it's a Latin word which is incorporated into chemistry and very much used and understood by chemists. So by in situ means that we are measuring the catalysts under specific conditions, like what happens during heating, cooling, or under the catalytic reactions. So this kind of spectroscopies are called in situ spectroscopies. And because many of our systems needs to be investigated under in situ conditions, most of the spectroscopies are now moving forward this in situ method or in situ way to understand or to investigate more and more and better. So not only the structures, what I was saying during a catalytic reaction or heterogeneous catalytic reactions, it not only restructuring happens, some related to the catalyst functioning, and we need to understand or investigate those phenomena. Like sometimes catalyst particles are leached out, means like they separate out and does not function anymore or any longer. And sometimes what happens that this Oswald ripening, we know that many particles or many atoms of catalyst surface, they come together and form, they sinter together and form a bulk particle which no longer takes part in the reaction. And in that way, the catalyst functioning may decrease. That's why we investigate the heterogeneous catalytic reactions more in an in situ matter. So today, before you, I present one of such spectroscopy, which is X-ray photoelectrode spectroscopy, or more popularly known as XPS, which is based on the effect of photoelectric effect, which was first explained by Hertz and then was properly explained by quantum mechanics by Einstein in 1905. So what happens in photoelectric effect? We all know that a photon, a sufficient energy of photons, it may be from X-ray, from UV, they interact with a metal, or they interact with a material, and then there is excitation of its electrons, which electrons are then ejected out and called photoelectrons. So if we analyze these ejected photoelectrons, the energy of these photoelectrons, we get many chemical information about that material, which first was proposed by many experiments from the scientist Kai M. Sigban from University of Uppsala, Sweden. For this, he was given the Nobel Prize in Physics in 1981, and his work led to this beautiful spectroscopic technique XPS for analyzing the chemical systems, and that's why many times XPS is also called ESCA. So if you see the spectrometer, X-ray photoelectron spectrometer, it is like there are main three components of a spectrometer. As I was saying, you need a X-ray source which shines or which emits a photon, mostly X-ray photon, or it can be UV photons from UV lamp, hydrogen lamp, helium lamp. And then you have electron analyzer, which analyzes the electrons, photoelectrons emitted from the sample. And the other part, which is a vacuum chamber, is called to place the samples and all these techniques together, all these components together. So why vacuum is needed, and this kind of traditional methods are not used for in situ spectroscopy. We need vacuum because we need vacuum because most of our components, these X-ray components or the electron analyzers, they cannot be put in a pressure. So that's why we have to protect them, and that's why this electron emission and this X-ray, all these things needs to be done in a vacuum. And this is the reason that this technique operates in very high vacuum, like 10 to the power minus 6 to 10 to the power minus 10 millibars or below, and that's why they cannot be used to investigate in situ chemical reactions. So how does a XPS spectra looks like? Like, this is a spectra obtained from titania surface. We all know titania is a very famous surface, very famous material, or very popular material, and to use for photocatalyst or different dyes or cosmetic products. So here you can see that the peaks from titanium 2p, yes, this is my cursor, yeah. So titanium 2p, oxygen 1s, and valence band, and the different kinds of other titanium core level peaks, and then Auger peaks. So these kind of peaks are appearing on the material, and that's why this technique is so much self-sustaining. Means like it can give you informations not only about the elements present in your sample. This is surface sensitive, and also it delivers the information about the oxidation states of the material, of different elements present in the sample. So I was working with the more advanced technique or the next generation of XPS, or you can say the in situ version of XPS. So XPS is, as I was mentioning, the traditional XPS needs very high vacuum, and it cannot be, that's why it cannot be used to study in situ reactions. But nowadays, over a few decades, people have developed XPS to do photoemission studies at elevated pressures, and this technique is called ambient pressure XPS, or we call it simply as in situ XPS, where they have used a developed differentially pumped analyzer, which can be used in more elevated pressures, and it is fitted with a nozzle. You can see this is a cone which has a very tiny aperture to collect photoelectrons. But in case of traditional XPS, this aperture is much larger, like 3 millimeter or 4 millimeter. But in AP XPS systems, to increase this efficient differential pumping, we are fitting a cone with a very small apertures, like micron sizes, like 500 microns or 300 microns or half a millimeter kind of things. And because it's a photon in and electron out spectroscopy, the presence of different molecules can attenuate the emitted photoelectrons, and due to this short inelastic mean free path of photoelectrons, we place the sample very close to the analyzer. If you can see my cursor, this, I am pointing at the sample holder, which is placed very close to the analyzer cone, so that this we can overcome this short inelastic mean free path limitation. And in this way, the photoemission process has, or photoemission technique has been improved to be able to do studies like few tens of millibars, or even people are nowadays going towards bars or atmospheric pressure or over atmospheric pressure to understand a in situ reaction in a very practical conditions. So what we understand from here is that this ambient pressure XPS is an excellent tool to study surfaces and interfaces in situ. Why surfaces and interfaces are much more interesting? Because this surface catalysis means surface reactions, or if you go to batteries or electrolytes, or if you go to different fuel cell membranes. So here, most of these phenomena or most of these chemical systems are made of I mean, many interesting chemistry, or most of the interesting chemistry is happening on the surfaces and interfaces. That's why we need a technique which is very surface sensitive. And XPS, one very important thing is that it's a very element specific. So you can tell about the element specific, what elements are doing and what is the oxidation states. So this kind of important informations can be obtained under operation conditions or in situ conditions. So nowadays, people are using AP-XPS in different kind of, I mean, all kind of interfaces, like gas-solid interface, which I was mostly working on, because most of the heterogeneous catalytic systems I was studying are solid systems. So most of these reactions are gas-solid interface. And then we can also do liquid gas. We can also investigate the liquid gas interface by using liquid microjet XPS. And then also we can probe electrolytes or battery, like the solid liquid interface, which I never worked, but I was participating in some of the experiments, and I have seen some of the systems where the solid liquid interface also working. And then in more advanced way, people are nowadays trying to improve trying to develop some membrane covered cells for in situ XPS, like graphene membrane covered cells. Why graphene? Because graphene is semi-permeable to photoelectrons. So people are using graphene as a membrane to make cells which can be used for homogeneous systems, or even systems at higher than atmospheric pressures. So APXPS can do all kinds of these interfaces, surfaces, or the cells, different kind of systems it can work with. So here are some of the APXPS setups I was working with. So during my PhD, I was using a laboratory-based APXPS setup at NCL Pune, which is fortunately the first APXPS system in India and probably the first or second of its kind in Asia. And then I was working in my first postdoc during 2015 to 2018 at a APXPS setup at Swiss Light Source in Switzerland, and then I moved to work with a different APXPS setup at Diamond Light Source in Oxfordshire, UK, which is here on the top right of this panel of this slideshow. So this in Swiss Light Source, this APXPS setup was used here in this X07 DB beamline. Here this setup is now presently situated. But when I was working, we were also using it as an end station to move to different beamlines for different kind of experiments. And this is the diamond light source. In here, the BO7, which is this is the entrance building, and this is just opposite to entrance building is the beamline BO7, which was housing this APXPS setup I was working with during my postdoc in 2019 to up to March 2020. So as we are talking about more of synchrotron sources, so many of us are very well known about synchrotron, but some of us may not are very familiar with synchrotron. So it's kind of like a simple, a large-scale facility, which a particle accelerator, like Large Hadron Collider, which is like a proton accelerator, but here it's the electron accelerator. And this, what it does is that it accelerates the electrons to around at the speed of around the speed of light, and in that way it emits different photons of different energies and with a very high photon flux, like very high bright source of photons with different energy range for giving to be utilized for different kind of instruments which need energy range of different variables. So I present before you a small introduction video of synchrotron. I don't know if that video plays. Probably is playing.
The linear accelerator, the booster, and the storage ring produce the intense synchrotron light required for the demanding experiments set to become the hallmark of this research facility. Electrons start their journey in the linear accelerator, or LINAC, and they're then transferred into the booster synchrotron, a 158-meter circumference stainless steel tube surrounded with magnets. Here they're accelerated to fantastic speeds in an extremely high vacuum, similar to that encountered in deep space. In the booster, they gain energy until, at nearly the speed of light, they are injected into the storage ring, over half a kilometer in circumference. As the electrons circulate around the storage ring, they pass through specially designed magnets called insertion devices. These cause the electrons to wiggle or undulate, producing intense X-rays, 100 billion times brighter than hospital X-rays.
Yeah, so these X-rays or different kind of photons are given to different beamlines where we have different kind of instruments like this, which we had. This is a APXPS end station of BO7 beamline at the Diamond Light Source. Here we were doing our experiments for ambient pressure photoemission. So how we do these experiments, I'm going to show you some of our sample holders or samples, how we put the sample in and how we do the reactions. So in the left panel, you can see that this is a sample holder with a copper plate and onto that is a silicon wafer coated with a sample, like powder sample. And this sample holder can be put inside the instrument near to the analyzer where the beam is coming. And here is a different sample holder. I was using a diamond. This has a copper the clips are attaching a copper plate, copper foil, and onto that there's a pellet of powder samples. You can pelletize your powder samples and put a stick onto the sample holder, or sometimes you can put directly drop cast your samples as a thin film on the gold foils. I mean, for most of my experiments, I was doing this simple drop casting on a gold foil because my samples were mostly powder catalyst and of nature of oxides, bimetallic particles, or sometimes the zeolites, which are very non-conducting. And if these samples are non-conducting, they cannot be probed with many of the XPS techniques, or many of the other, like electron transmission, electron microscopy, those kind of things cannot be utilized for these non-conducting samples. And that's why we are putting a very, very thin layer of powder samples on the gold foil. And these sample holders go into the sample manipulator here. Probably I hope my cursor is visible. It goes here, and from one side, this is 2, from one side the beam comes, the X-ray photons come, and it shines on the material, shines the catalyst, and the emitted photoelectrons are then collected, or are then goes to this electron analyzer through this tiny aperture of the photoelectron analyzer. And during these experiments, we dose different kind of gases which are relevant reactants, and we also can analyze the products with mass spectroscopy. So this is the setup for gas solid reactions. And people are also using, like, this is a setup for liquid microjet used in the Swiss light source liquid microjet end station. Here you can see that we can see that this liquid microjet of around 20 to 30 micrometer is produced, and these liquid microjets can be, so X-ray, this is one is a X-ray window, which is a silicon nitride membrane. So X-ray comes from the synchrotron through this window, shines on the liquid jet, and then electrons are collected through this small aperture of the analyzer cone. And in this way, we get informations about the system, or we investigate the system in this way. So I'm not going into many technicalities or technical discussions, which is beyond the scope of this presentation or of this webinar. So today I am going to give you some of the scientific experiments or scientific systems, heterogeneous catalytic systems, that we have studied during my postdoc with APXPS system. The first one is a guaiacol deoxygenation on platinum bismuth bimetallic nanoparticles on carbon. This reaction is, or this system is very important because it shows the bio-oil deoxygenation, and it also highlights how we can prevent the catalyst deactivation. And then I show you, sorry, I show you the carbon monoxide and oxygen, carbon monoxide oxidation to carbon dioxide with oxygen, with a very commonly known catalyst on platinum on ceria. So this is very important, though the reaction is very simple, but we had shown here the time resolution activities of XPS, and we first time showed that with a XPS kinetic time resolution of catalysis, we can distinguish between spectators and active species in a catalytic system on a powder catalyst. And then at the last part, I will be talking to you, I'll be presenting to you on the spatial resolution in XPS, like many modern systems which are much more well defined and microscopically heterogeneous surface, like grain boundaries or nanoparticles, we need spatial resolution. Like generally what happens that when we do traditional XPS, we generally probe millimeters of surfaces, or we see the 1 millimeter by 3 millimeter of the catalyst surface, which is kind of like a maybe very broad area for many of the specific catalysts, and we need to see much more closely or in a spatial resolution way. That's why we need to develop some kind of technique which can be probing like in micrometers or nanometer level of spatial resolution. So we move on to discussions. Please be with me. So first system, we are talking about the deoxygenation of bio-oil. Bio-oil is not like when we nowadays people are trying to get non-conventional source of energy or fuel by pyrolyzing lignocellulosic biomass to produce bio-oils, but these bio-oils cannot be directly used as a fuel. They need to be converted because of their high oxygen content, and we need to do deoxygenation, like reduce their oxygen contents to get fuels to use them as a fuels. So far now, I mean, researchers were using hydrogen, pure hydrogen, to do this hydrodeoxygenation of bio oils. But pure hydrogen itself is very costly, and it is very costly, and to get pure hydrogen, it's not very easy. Not very easy, I wouldn't say. I mean, it's very costly. Rather than if you can find an alternate way, like not using hydrogen but using methane, which is much more cheap and is much more available, and it is kind of like burnt away every year in the oil sites. We can use oil mining sites. We can use this methane as a replacement of hydrogen, as a source of hydrogen to do this kind of reactions. This is a very smart way of utilizing methane as well as converting biomass into fuels. So one of our collaborators from University of Padua, they were working with a catalyst at 5% platinum on activated charcoal, which is a very efficient, a very good catalyst for doing this kind of reactions. Guaiacol, guaiacol is a kind of like model component of bio-oil, and they were using the reaction with methane to get a very good conversion with using 5% platinum. But with 5% platinum, if you see the red curve on this reactivity data, the catalyst deactivates within few hours. Within 3 to 4 hours, the catalyst deactivates. So we need to look into a system which can improve the activity of these catalysts, and we found that 1% bismuth platinum bimetallic binary system on activated charcoal can be a very promising catalyst, because it is, if you see these curves, like a black curve and the blue curve, the catalyst is stable for a long time without being deactivated. So what happens during this deactivation process? We were trying to understand with APXPS system, and these are the results from, I mean, it's a very brief and synopsis of these results. So here you see on the left hand side the bismuth core level photoelectron spectra acquired under various conditions, various reaction conditions. Like here, the catalyst was first introduced, and we call it as such spectra. Means like just catalyst is dosed with a helium gas which doesn't react. It's a noble gas, and then we activate the catalyst by reducing with hydrogen. So this is the spectra for activated in hydrogen, the catalytic bismuth spectra, and then we dose different reactants like methane, and then methane plus guaiacol, and also only guaiacol, like we replace methane with helium. And during these studies, for time resolution studies, we found that the right hand panel, if you see the quantification curve, if you see that under methane and guaiacol, I mean under the presence of both reactants, the bismuth oxidized bismuth, this is the, on the left hand side we have the plot of oxidized bismuth and metallic bismuth ratio. It shows a very small amount of oxidized bismuth in reactive condition, but when we remove the methane and we put only guaiacol, it shows that the amount of oxidic bismuth is very high, or goes into a peak, a maxima. And then when we put another dose of methane and guaiacol, this ratio comes down very much. I mean, it comes down to the previous, that bismuth here in the binary system acts like a sacrificial oxidized. Actually, this guaiacol or this kind of bio-oil components, they have very high oxygen containing groups which are prone to oxygenate most of the catalysts. And by oxygenating the catalyst, it deactivates its function. So once platinum is oxidized, it doesn't function anymore any good as a catalyst. So in this binary system, and that's why the catalyst is deactivated. But when we use bismuth itself, like a friend or sacrificing agent, it gets oxidized much more than platinum, and in this way protects the oxidation of platinum. So this kind of valuable informations or this kind of systems we can investigate through this. I mean, I must say it here, or I should say, like technically or technologically, this kind of analyzing or investigating this kind of systems is very, very challenging, and not many facilities in the world is available to study this kind of reactions under in situ conditions. So in the next topic, we move to the CO oxidation on platinum ceria catalyst. So platinum ceria is a very well-known catalyst for low temperature CO oxidation. And during this CO oxidation, what happens? I mean, generally researchers used to study the amount of, used to analyze the amount of cerium 3+, because in ceria the oxidation state of cerium is 4+, and then it also goes to a redox couple like cerium 4+ to 3+, and then again comes back to 4+. So researchers used to say that this 3+, what is present in ceria, cerium 3+, amount of cerium 3+, this is the active site for this kind of reactions, like carbon monoxide reaction on ceria catalyst. But all of these cerium 3+ sites, what we find in our reactions, in our studies, is that not all these cerium 3+ sites are active sites. So here what we do is that, so how do we do this analysis, is that we have, this is a sketch of our reactor cell where you can see different components. It's like a small, very small, like a reactor kind of cell, where this gas flow comes from the upstream with the very mass flow controllers. You can control the different reactant gases, and in the downstream there are pumps. In the downstream there are pumps connected, which pumps out all the reactants and products. So it's a very dynamic or flow conditions, and in this way, I mean, we develop this system so that we can do a very quick gas switch between reactants and other reactants within 20 seconds or even 10 to 20 seconds. So basically what we try to do here is that we find a steady state condition like CO plus O2 on platinum and Syria catalyst, and then in the steady state condition we analyze the different ratio of cerium 4 plus and cerium 3 plus, and then we switch to a different gas mixture, a different reactant mixture, like it's a neutral mixture, like by removing oxygen and putting only nitrogen. So from CO plus oxygen to CO plus nitrogen. So we fluctuate, or we move the system from steady state to transient state to steady state to transient state, and in this way we study the evolution of different cerium 3 plus species in different conditions. And what we found, if you see, for simplification, I will tell you, you can follow this top right corner. This is the ratio of cerium 3 plus and cerium 4 plus in this catalyst, and we see that there is a delay time of around 2 minutes, or at the end of around 2.5 or 3 minutes, we reach to a maximum of cerium 3 plus ratio. So it means that there is a cerium 3 plus in a steady state condition, but the moment you move back to a transient state, there are some more cerium 3 plus in the system. It means that not all the cerium 3 plus is active for this reaction, but some of the cerium 3 plus are just spectators, or they don't take part. They're present, but they don't take part in the catalytic reaction. So why this happens? Because here the platinum is the active metal which splits CO, or which also splits oxygen, which binds oxygen and CO and splits them. So most of the cerium 3 plus we are attached, which are very close or chemically attached to platinum, they are the active sites, and the cerium 3 plus which are placed in a far away from the platinum species are not very active in these catalytic reactions. And at the last part of my talk, I'll be talking about the spatial resolution in XPS, which is important to understand many microscopically heterogeneous systems. Like we were developing in Swiss Light Source a nano XPS chamber, and this chamber has a unique geometry. Like generally in XPS, you have the photon source and the analyzer in the same side of the catalyst. But in this system, we have put the analyzer in the transmission mode, like after the sample. So why we did this kind of things? Because we had a plan to test a system in such a way that they have silicon nitride membrane on one side and graphene membrane on the other side. Because see, silicon nitride membrane is transparent to X-ray, but it is not transparent, not permeable by photoelectrons. And the graphene membrane, they are permeable for photoelectrons, but they are not very good, efficient to maintain a vacuum or to maintain a pressure barrier, which is very, we have to maintain a pressure barrier of few orders of magnitude in this kind of experiments. So what we were doing is that we were using a Fresnel zone plate to focus. The Fresnel zone plates are, circular interference species, which does the interference of X-ray beams and produce very focused X-rays, like beyond our imagination, like in a few nanometers, or within the range of nanometers, micrometers. This kind of focusing we can obtain by using zone plates. So by using these zone plates, we were focusing X-rays to a very, very narrow beams, like few nanometers. But during this commissioning experiments, we were focusing around 500 nanometer to get a very good spatial resolution. And here you see the real pictures of different components. So these are on the left hand side, we have this assembly of zone plate here. This is the Fresnel zone plate. And then we have a order sorting aperture, which sorts the zeroth light coming from the zone plate, which needs to be sorted out. And otherwise, these are not the focused X-rays. So we sort it out. And then we have a sample holder, which has we use 9 samples, which are very thin. Obviously, this should be very thin membranes. Otherwise, we cannot do the transmission mode XPS studies. And all these motors, all these components are placed on top of motors. These are piezo motors, like from a company Smaragd. We call them Smaragd motors. And these motors are highly precise, like in a nanometer resolutions, and they can be controlled by computer programs from outside the chamber. And on the back side of the sample here, you can see we have photodiode to detect the to detect the current, to record the current emitted from the transmitted from the sample. And in this view, we can also see the analyzer. This is the top view. This is the photodiode. So this is a zone plate. This is order sorting aperture, then sample, and this is the analyzer, and here is the photodiode. So these are the main components of this system. And by using this kind of setups, we can go for very high resolution of very high spatial resolution of XPS spectra of different samples. So for our commissioning experiments, we were using some copper microstructures deposited on chromium covered silicon nitride membrane. These were made with a pulse layer deposition technique. And these copper microstructures are like islands, like they are different shaped islands on this silicon nitride membrane. And these are 2 images we simultaneously recorded from our setup. So this is a 10 by 20 micrometer area of the sample, where you have a current image. On the left hand side you have a current image, and on the right hand side we have the photo emission image. So by analyzing these images from their line profiles, we can see that we can detect. So these 2 images are like complementary images. Like for current image, the darker spots are the particles, where these copper particles are present on the silicon nitride membrane. And on the right hand side, the photo emission image, this is a complementary picture, like the bright spots are the particle, and these bright spots are the copper particles. And that's why this line profile these are XPS intensities are positive and currents are negative. So in this way, we can see that we can locate exactly the positions of the microstructures, and this resolution is very high, to the 500, as I said, 500 nanometer of resolutions we can find from this kind of experiments or this kind of setups. After I left, now they're trying to improve the resolution even to a higher nanometer side, like few tens of nanometers. And in this way, we can develop much more spatial resolution of XPS, which will be coming in future days. People are working on this topic, and many people, not many people, but few people around the world are working on this side of XPS. And fortunately, or maybe in future, we will be also seeing that in commercial sector. And from this XPS images, we can also extract the information of individual XPS spectra. So our analyzer, if you see my cursor, so these are the images, black and white images of scans, position of scans. So this analyzer, what we were using is a 2D delay line detector. So it can it records the spectra in it records the data with 100 channels, physical channels. So by line profiles of these channels, we can extract the information of spectra, XPS spectrum. So this is the XPS spectrum of 187th line, 187th line, yes, where we know that there is some copper structure, and we can see that it's a XPS peak of around 123.3 EV, which corresponds to copper 3s in ionic form, obviously, because we know that copper is very much oxidizing when it is exposed to air. And these films, after making them in laboratory, we had brought these samples and exposed to air, so it's very likely that copper would be in a copper ionic state. So with these results, I am coming to the end of my slides, end of my presentation. So what I presented before you is some of my work, which are very relevant and which are very contemporary. People are working nowadays towards heterogeneous catalysis, not only heterogeneous catalysis, people who are working with electrocatalyst or battery or different kind of fuel cell membranes or solar cell photocatalyst, they are gradually moving toward the in situ understanding of their systems, because in situ understanding or in situ investigation is very important to know what actually going on the surface or going on in the system. Yes, so I also try to invoke some interest in you or some students if they're listening. At the end, I acknowledge my PhD supervisors from NCL Pune, Dr. Gopinath, Chinakonda S. Gopinath, and then postdoc supervisor, Professor Yeun van Bokhoven from UT Zurich, and Professor Georg Held from Diamond Light Source, UK, and my colleagues and co-workers with whom I worked, and their presentations are, their works are presented from their work I have presented here. And at the last of all, I thank all of you who are listening to me and the organizing committee for organizing these kind of webinars. Thank you very much. Over to you, Anup.
Thank you, Professor Konuk Roy, for your nice presentation on XPS studies on heterogeneous catalysis. This is the time for the question answer session. Professor Chirantan Hajra from our college has a couple of questions for you. I am requesting Professor Chirantan Hajra to ask you the questions directly. Professor Hajra, please.
Yes, please, Hajra. Yeah, it's an interesting question. Actually, you know that the magnetic fields interrupts with the photoemission process, right? That's why most of these XPS systems are shielded with mu metals. Yeah, because there should not be any magnetic field. So if the material itself is paramagnetic or magnetic in nature, it might interact with the magnetic field of the system, of the chamber, but I think it is not very much important or very much significant, because when you have paramagnetic materials and you use a very small amount of sample, the magnetic field generated by this kind of samples are very, very low. Like you can tell about Bohr magnetron or different units is a very, very low amount of magnetic field. So it doesn't change much with the XPS analysis. I mean, we also detect ferric oxide or ferric nitrate. I mean, different iron samples we can analyze with XPS, yeah, without any problem, yeah. Yeah, we can, yeah, yes, yes, yes. Mm-hmm. 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 See, we do not study the magnetization state with XPS. You do not get any information about the magnetization. And if you are thinking about the change in your sample due to XPS, I don't think the magnetization effect is very significant, because I told you that this is a very low amount of magnetic field in your sample, so it doesn't matter much. But in terms of oxygen vacancy, I must say that sometimes we have seen, even in NCL also, we have seen that if you have, I mean, nowadays most of these XPS are micro-focused XPS source. Okay, so if you have dense micro-focused X-ray source, this can create oxygen vacancies, or this can reduce your samples. That's for sure, yeah. Mm-hmm. 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 Yes, it's possible. Yeah, it's possible. Yeah, I like to add one more sentence, is that, see, the time resolution or the time scale, if you see the molecular dynamics time scale, which is like femtosecond or picoseconds, okay, which is, but if you see the catalytic systems, it is like in minutes. Like the oxidation state of copper may change in minutes or in hours, okay. So you can constantly monitor with XPS the change of oxidation states by, I mean, in real time. Yes, in the sense of real time means like in minutes or in hours. Definitely you can. Yeah, yeah,
Uh, Dr. Rai,
yeah.
Dr. Rai, we have a question. What type of results do we get when if XPS analysis is done on gold nanoparticle or silver nanoparticle when capped or embodied by some sugarcane or glucose? What type of result we will expect?
Yeah. Okay, so you can expect from XPS, you can expect the the oxidation state of gold or oxidation state of silver, okay, and then based on different capping agents, this amount of oxidation or amount of reduction can be different. Like suppose I give you one example. Like during my PhD, we were working on a pyrrolene diimide sample, okay, nitrogen based ligands, and we saw that with change of different ligands, the oxidation states are not different. I would not say that it's +1 or +2, but within +1 or within +2, they're changing by a small amount of uh, small amount, like maybe 1 eV, about 0.5 eV electron volt, which is the binding energy scale of XPS. So you can say that for different ligands, the amount of oxidation or amount of reduction is changing. That's one thing. And you can also do depth profiling. By depth profiling, you can say that your gold nanoparticle is buried under, or it's capped with the ligands, or it's outside the sample, or it's not capped with the ligand. So these kind of different informations you can get from XPS.
So that is mainly we can get oxidation state, whether it is in zero oxidation state or +1 or etc. Or we can do not get any morphology of the state. Only we get oxidation state.
Yes, morphology you can indirectly say, but not exact picture like same or 10. This kind of picture you cannot get. You can say about the element and its oxidation state, its environment. Yeah.
Okay, thank you, thank you.
Yeah, yeah, yeah.
Okay, Professor Roy, there is another question from the participant. The question is that, is there any limitations of XPH and why it cannot detect hydrogen and helium surfaces?
Why it cannot?
Detect hydrogen and helium surfaces.
Ah, okay. Generally, the helium, I mean, whoever asked, it's a very interesting question. Yeah. I mean, like, we were not detecting hydrogen or helium previously, but recently people have reported hydrogen and helium as well. I mean, for your information, I should mention it. Like previously, in XPS, hydrogen or helium was not being detected because they have a very low photoionization cross section. So photoionization, by photoionization cross section means like how does an element or a material responds to the incoming X-rays, or how does it responds to the photo emission process. It's called the photoionization cross section. So for hydrogen and helium, the photoionization cross section is very low, and that's why they were not being detected. But this was the case when people were using traditional XPS. It means that they were using aluminum K alpha source, which gives a photon of 1486.6 electron volt. But nowadays, recently, if you want, who has asked the question, if they want, I can send them a link where people have reported the photoionization spectrum of, I mean, photoelectron XPS spectrum of hydrogen and helium as well, by taking one bar around hydrogen and helium. That's the beauty of APXPS. Like people are now doing many challenging things which were not possible earlier. Yeah.
Okay, thank you, Professor Rai.
Yeah.
At this moment, there is no more question for you. And in this case, great thanks to you for your time and for your nice presentation. I hope the participants have enjoyed this lecture very much.
Yeah, thank
I
you.
would
Thank you for having me. Yeah.
I would like to thank the speakers, Dr. Madhusudan Maji and Dr. Kanak Rai, for their time and for sharing their knowledge and their works with us. And I also would like to thank all the participants for their patience and bearing us for last 2 hours. It's the time to call it a day for right now. And this webinar will continue tomorrow, and hope we will meet again 11 a.m. tomorrow. Thank you all.
Yeah. Thank you.
Thank you, Anup. Thank you. Okay, bye-bye.